Okay, so it's time to start. It's my pleasure and deep honor to introduce our first speaker today, Professor Alan Frieze. Professor Frieze was born in London, England, and after education in Oxford and University of London and a span in England, he moved to the US, where he's now at Carnegie Mellon University. Professor Frieze's main interest in mathematics lie in combinatorics, optimization, and theoretical computer science. He's one of the foremost experts in the area of probabilistic combinatorics and randomized algorithms. Among his many achievements, just let me mention one today. This very simply stated problem of computing volume of the convex body, which you can easily imagine. This problem is extremely hard in high dimension if the convex body in high dimension. And Professor Frieze was the first to design polynomial algorithm, namely a quick algorithm, efficient algorithm, that approximates the volume of any convex body in any dimension, for which he was awarded the Ferguson Prize in 1991. And today he's going to talk about randomized structure and algorithms. Professor Frieze.
Okay, so thank you very much for that nice introduction. And I must thank the committee for inviting me to give a talk here. It's obviously a great honor, and I'll do my best, let's say. Okay, so I'm going to talk about random structures and algorithms. So what does that mean? So I'm going to talk about some combinatorial questions with a sort of a probabilistic flavor. And I'm also going to try and look at some algorithmic questions associated with this sort of problem. Okay, so that's what I'm going to talk about, right? So that's the list. I think it's too long. I mean, they give you a year to think about this, and if you think about it for a long time, you come up with hundreds of slides. And so I've left some of these slides back home in Pittsburgh, and I brought twice as many slides as I need. So, but I won't keep you here till 11 o'clock. I don't want to worry the next speaker. So let's talk about random discrete structures. Okay, so when I first thought of this slide, I have to put everything into some sort of context. And so what I thought I would say was that combinatorics or discrete math, and I put in the main, concerns certain properties of I can see it here, of certain large finite sets with some mathematically defined structure. So of course you can put combinatorics on infinite sets, so that's sort of all going by the board. And then I thought I'd sort of divide the area up into three pieces, but I've obviously left out a lot of the stuff, so this is, anyway, that's three pieces. So once you've defined this set, you sort of think of questions about it. So let's say this set is omega. Often it's a set of graphs or a set of permutations, and there are certain very natural questions to ask about it. For example, you could ask, how big is it? And if you're interested in how big the set, well, first of all, I suppose you want to know, is it non-empty? But assuming it's obviously non-empty, you want to know how big it is, and I suppose that would fall into enumerative combinatorics. So I won't say any more about that. Another thing you could say is, how big is the greatest, in quotes, element of this set? So that would fall into the realm of extremal combinatorics. But I'm not going to talk about that either. So what am I going to talk about? So I'm going to talk about what are the properties of a typical member of omega. So this will be probabilistic combinatorics. So if I say typical, what that means is that I put some probability distribution on the set of members of omega, and I draw a sample. And I'd like to know what it looks like. And sometimes you can predict some of the properties. And so I did say and algorithms. So associated with a lot of these questions are computational problems, like even how big is omega? That could be a computational question. You want to count approximately the number of elements in this set. So the analysis of algorithms aims to find the complexity of some of these computational problems. And I shall be looking at the analysis of algorithms in relation to bullet 3. So I'm going to talk about the average case. So often in analysis of algorithms, people focus on the worst case, and I think most people do focus on the worst case, but there is some interesting work to be done on the average case. So what's next? I hope this is the right set of slides. Okay, so also there's an associated topic called the probabilistic method, where you use probabilistic tools to prove deterministic results, as sort of pioneered by Paul Eredosh. Okay, so that's got the introduction out of the way. And what I will talk about next is an instance illustrating the average case analysis of an algorithm. I'm going to talk about the traveling salesperson, or the TSP in the unit square. But first of all, I have to put this into some sort of context. Okay, so we use computers to solve many problems, optimization problems, and it's unfortunate that, I don't know, I'm looking there. So it's unfortunate that many of these problems turn out to be hard in some well-recognized sense, and the sense is NP hard. But when you say NP hard, you mean that the worst case. You mean this problem is such that at the moment, for any known algorithm, I can find a case that will make it run for an enormously long time. But these problems appear in the real world and are solved, so there must be some reason for this. And it's important to try and explain this, maybe come up with ideas that will help solve these things more efficiently. So it's probably better to try and focus on, well, you can focus on the average case. As I said, sort of typical problems are often easy to satisfactorily solve. Now, unfortunately, sort of to do the mathematics on it, one has to assume some totally unrealistic distribution. So even if the worst case is not really realistic, uniform distribution could also be unrealistic, but the mathematics is quite interesting, so that's what we do. Okay, and so as Richard Karp pioneered the idea of finding algorithms that work well in the average case, not to focus on just the worst case. I mean, he'd already sort of let us down by telling us that there are so many problems that are hard in the worst case, and this was a sort of compensation. This is, don't just focus on the worst case, let's try looking at the average case. So are we looking at the unit square? Okay, so this is the unit square, and you'll see some dots in the unit square. And what are these dots? These are randomly chosen points, and there are n of them, and they're all chosen independently, and let's say they're chosen uniformly at random inside this square. Okay. Okay, so an early result was by Beardwood, Holton, and Hammersley. And the question you ask is, you generate these endpoints at random, and you let Z, or Z, be the minimum total length of a closed path, which we'll call a tour. This is supposed to be the path taken by a traveling salesperson who wants to get home as quickly as possible, but visit all the points. And we want to consider how Z changes as n grows to infinity. And the main result of Beardwood, Holton, and Hammersley was that Z divided by the square root n tends to beta. some constant as n tends to infinity. This happens with probability 1. And they actually did it for more than just a uniform distribution. They did it for any old distribution in the unit square, as long as the points are chosen independently. What is strange is that so this is what, over 50 years since this result was mentioned, and there are people working in this area, but the precise value of beta is still not known. So basically, their proof, you use some argument to show that the limit exists, but it doesn't tell you what the limit is. And this is generally true of many questions like this in the unit square. You can prove that the optimization problem or the minimization result grows like the square root of n, and there is some constant, but you don't know the constant. And I don't even think sometimes you can't even compare the constants, or it's hard to compare the constants. Okay, so we know if we generate this problem uniformly at random, it's actually a hard problem. It's still NP hard if you do it in the worst case. But if you do it at random, you actually know what the answer is. At least you know the optimization, but you don't know what a good tour is. So Karp suggested what he calls a partitioning heuristic, a very simple idea, although this is a little bit simpler than he was proposing. I think he wanted to speed it up a bit, but this is a pretty simple idea. So what you do is you partition the square into little subsquares of area roughly log n over n. And then what you do is you expect in each square there to be about log n points. Okay? And then you can argue that with high probability, in other words, with very probability close to 1, that every square contains order log n points. And then what you can do is you can use dynamic programming. It's an algorithm invented by Held and Karp, which runs into exponential time. But if it's exponential in log n, it's only polynomial time. So you can actually find the smallest, shortest tour inside each square. And now you've got the shortest tour inside each square, what do? Well, you just sort of connect them up in a sort of chessboard pattern. You sort of go up like this, right? And you don't take any care at all, other than you go up and then down and up and down, and you don't worry about which ones you connect. And then having done that, you delete a few edges, and you end up with a tour. Now this tour is obviously not optimal because there are crossings. In any optimal tour, there are no crossings. But you can actually argue that this is good in the following sense, that the total length of the edges I add is little o of square root n, and then another argument will tell you that with high probability we have found a tour which is 1 plus little o1 times the optimum. So there's a question there. So there's sort of two open questions, I think, for this problem. One would be to find beta, which is obviously extremely difficult. And the other would be, if we look at the error in Karp's algorithm or Karp's idea, it's n to the half minus little o1. And it would be interesting if you could find an algorithm which gave a tour where the error was n to the alpha, where alpha is strictly less than a half. And if you did that, you may be able to figure out what beta is, because you'd have to use some different idea. Okay, so that's all I wanted to say about the unit square. So let's move on to another area of interest, random graphs. And let's talk about evolution. Okay, so I wasn't sure. I assume everybody knows what a graph is, but obviously I didn't assume because I put one up. So this is a graph, a small graph with vertices and edges, which are just pairs of vertices. And this is the complete graph, where you join every pair. So first thing to mention is how do you choose a random graph? What do we mean by a random graph? Well, there's the classic Erdos-Rini graph, which has vertex set 1 to n, and it has m random edges. That's G and m. There's the independent model, which is G and P, So usually in math, changing m to p doesn't do anything, but in this subject, changing m to p does do stuff. So here p is the probability, and each edge of the complete graph is included independently with probability p. And this is, I think, first mentioned by somebody named Gilbert. And they're obviously related. GNP has roughly n choose 2 times p edges with high probability. If p is a half, you get each graph equally likely. One important point here is that if m is close to n choose 2 times p, then GNP and GNM have very similar properties. So even if you want to prove stuff about GNM, you can work with GNP and then translate the results. Okay. So now evolution. Okay, so Erdos and Rini in a seminal paper in 1960, which I suppose started the subject of random graphs, considered how the random graph grows as you add more edges. So we call this the graph process. And the graph process, you start with the empty graph, which is this collection of dots. It's the empty graph. And then you obtain gi plus 1 from gi by just adding a random edge. And what is interesting about it is that if you know how many edges you've added, you can sort of predict with high probability what the thing looks like. So for example, if you only add little o of square root n edges, then it looks like this, which is a bunch of disjoint edges. And the little o square root n is basically this birthday paradox thing. And if you just go a little bit past little square root n, say omega, where omega of n is just something growing a little bit faster, then what the graph looks like is you have still mainly isolated vertices and still mainly isolated edges, but small pieces with, instead of just one edge, things made out of 2 edges appear. Okay. So these are the components. And well, I suppose if you use your imagination, you can sort of imagine that this is the very earliest stage of the evolution of some life form, and you've just got single-celled creatures, and then you wait a little bit longer and you get slightly more complicated creatures with 2 cells. And if you wait a little bit longer, then you start getting creatures with 3 cells and so on. And it's not actually realistic, but it's a nice idea, a way to think about it. So to do that, that was the picture of it. So in words, if you have little o square root n edges, then they're all isolated. If you go faster than square root n, you get isolated edges and vertices and piles of length 2. And these actually are not difficult things to prove. And you go into 2/3, you get all these things. And the most likely thing is an isolated vertex, then there are more. The next most likely thing is an isolated edge, and so on. And in fact, if you go to n to the k minus 1 over k, then the components, you get trees with k edges and k plus 1 vertices. And every such thing will appear with higher probability. Okay, so this is the regime where the number of edges is sublinear. So it's little o of n. So the next question you would ask yourself is, what does it look like if we have a linear number, constant times n, in fact it's half Cn, and where C is less than 1. This is called the subcritical stage, and what you get are mainly trees, and the size of the largest component is order log n. Now if you jump from C less than 1 to C bigger than 1, what happens is that a giant component of linear size will emerge. And all the rest of the graph will just be a bunch of small components up to a size order log n. In actual fact, if you rip out the giant component, you sort of have a random graph with different parameters. So that's C less than 1 and C bigger than 1. And so what happens if C equals 1? Well, it is much more complicated or more fascinating. Here what happens is the maximum component size is of order n to the 2/3 and has been the subject of much more intense study. It's a more difficult, regime, let's say. So this is what Erdős and Rényi called the double jump. So you jump from log n to n to the 2/3 to linear size. So nowadays we mention this as the phase transition. Okay, so we keep going. We keep adding more edges. Eventually, you're going to get the complete graph. So eventually, the graph is going to be one piece. It's going to become connected. So the question is, when will it be connected? Oh, sorry, I missed the slide. So we do actually know what the size of the giant component is. It's n times gamma of c, where gamma of c is the survival probability of a Galton-Watson process where the number of descendants is Poisson with mean c. So when c is bigger than 1, gamma of c will be positive. And it sort of makes sense if you think about doing breadth-first search from a vertex. If the breadth-first search dies out, that's part of a small component. If it sort of grows to be large, which happens with probably gamma of c, obviously the things that this is finite, so this thing can't grow forever. So it grows into something big, and all the big things will actually join up together to make one giant component. So this is what it looks like for C constant C bigger than 1. And actually, this was a paper which Erdős Rényi did before the evolution paper, which was to find what we call the connectivity threshold. How many edges do you need in order that, with high probability, the random graph GNM is connected? And you can say that with remarkable precision, right? If you put m equals ½ n times log n plus cn, then you can find the limit of the probability that it's connected. And if you look at the picture below, this is supposed to indicate that there's a sharp transition from disconnected to connected. What I mean by sharp is that it's sort of linear in n to go from disconnected to connected, whereas it takes you sort of n log n to actually get to this point. And so a lot of random graphs is involved with, you take a graph property and you ask yourself, well, how many random edges do I need in order to guarantee that property with high probability? And what we're doing is we're looking at the thresholds. Okay. Yeah, so here's a very short proof it's a pretty trivial proof, but it does illustrate a couple of ideas. So let's suppose that P is 1 plus epsilon log n over n, and we would like to prove that this graph is connected with high probability, or in other words, that it's disconnected with very low probability. Now, it's difficult actually to compute the exact probability that it's disconnected, because you have to be able to count the number of connected graphs with a certain number of edges, and that's difficult. So instead of trying to compute this thing exactly, what we do is we say this property of being disconnected is contained in the union of some simpler events. And then we show that the union of the simpler events is of low probability. And so the art is to actually figure out what what the simpler events are. Okay, so here there's no art, it's pretty straightforward. You say if it's disconnected, then there must be a component of size between 1 and ½ n. And you just want to say that there's very unlikely to be a component of size between 1 and ½ n. And so what you do is you you sort of estimate the expected number of components of between 1.5 n, and then some simple estimations tell you this goes to 0. Okay. So this is called the first moment method, and it's a basic tool for the area. And what you usually do is you use this to get rid of the events of no consequence, and then you have to use other tools to sort of sort out the more difficult stuff. Okay. Okay, so let me just continue the evolution for a little while and talk about matchings. So a matching in a graph is just a set of disjoint edges. So the red edges are the matching, and the matching is perfect if it covers every vertex. And then a Hamilton cycle, here's a graph, and a Hamilton cycle will be a cycle which goes through each vertex once and only once, like the red thing. And so the question is, obviously the complete graph has a perfect matching, and the complete graph has a Hamilton cycle. So the question is, how many random edges do you need to add in order to guarantee one of these with high probability? Okay, so we're back to the graph process, although we haven't actually left it. We're back to the graph process, and so this is imagine that m is time, and let's say mk is the minimum time, first m, for which every vertex has degree at least k. That's mk. So clearly, to have a perfect matching, every vertex has to have, let's stop. Clearly, to be connected, every vertex has to have degree at least 1. And so you can rephrase the Erdős and Rényi result of 1959 to say that, I mean, in principle, you could get minimum degree 1 and then wait a bit to get connected. But the Erdős-Rényi proof says that with high probability, as soon as you have minimum degree 1, it's connected. And then a subsequent paper took a bit longer to prove, it was much more difficult, is also M1 is the time when you have a perfect matching. Okay. Because you need every vertex to have, at least one edge before you can get a perfect match. And you need even number of vertices, obviously. But M1 is the time when GM first has a perfect matching. So the Hamilton cycle question was more difficult, and it took quite a while to figure out, because in the 1960 paper, one of the main open questions was when is there what I call it a Hamilton line. So when is there one of those? And that was answered by Oitoy, Komlos, Semerady, and Bolabash. And it's also a bit surprising that you just have to wait until the last sort of laggard vertex has minimum degree 2. And as soon as every vertex has got degree 2, you have a Hamilton cycle with high probability. And so let me focus a little bit about Hamilton cycles. In fact, what we showed with Cooper was at this same time, it's not just one Hamilton cycle, but you get a large number of Hamilton cycles. In fact, log n to the n minus little o n. Now, you can't prove this by taking the expected number of Hamilton cycles and computing the variance and using the Chebyshev. That sort of doesn't work. That works, but later on in the game. That works when the number of edges is growing faster than n to the 1.5, and then the Chebyshev inequality will kick in, and you can prove a sort of central limit theorem or log normal or something like that for distribution. So it has log n to the n minus little n. I thought this was, sometimes you prove results and you don't think anybody's going to improve them. I mean, there's only a little o n to work with, but recently Glebov and Krivalevich showed that in fact the log n to the little o n could be replaced by e to the little o n. Okay? So I don't know whether this is going to be continued and maybe replace e to the little o n by a polynomial or a constant. And the other thing is, if you are interested, you could try and figure out what the distribution of the number of Hamilton cycles is. Okay. I say there are lots of them. So what other questions can you ask about Hamilton cycles? You can say, well, how many edge disjoint Hamilton cycles can I find? Well, if you have minimum degree k, and k is even, then you can't get more than k over 2, because each Hamilton cycle takes up 2 edges. Well, with Bolabash, we proved that you can actually get k over 2 disjoint Hamilton cycles, but this was only for k constant. And if k is odd, you can get a half a Hamilton cycle. So in this game, half a Hamilton cycle is a perfect matching. And so I mean, I can't speak for Baylor, but I didn't think that this was the end of the story. See, there's a restriction here on mk that k is a constant. And in some sense, it should get easier as k grows. But in fact, the proofs get harder, or at least our proof just completely breaks down. And very recently, two groups have solved this problem. The first is Knox, Kuhn, and Oosters from Birmingham, who proved that basically if the number of edges m is reasonably large, n to the log to the 50th, obviously they weren't really trying to figure out what the 50th was, then the random graph with high probability has a delta over 2 Hamilton cycles, edge disjoint Hamilton cycles, and a perfect matching if necessary. And I think around the same time, a little bit later, Krivolevich and Samoti finished it at the lower end. So now it's completely solved. And these are quite difficult papers. So let me talk about another area, the chromatic number. Okay, so what's the chromatic number? So you have a graph and you want to color the vertices in such a way such that every pair, so if you take an edge, the colors appearing on the edge are different. That's a proper coloring. And the minimum number of colors needed is called the chromatic number. So, I mean, obviously a natural question then is what is the chromatic number of a random graph? Right. Okay, so if you think about it, the vertices which are red, okay, there's no edges between them. And a set of vertices which do not induce an edge is called an independent set. So alpha G is the size of the largest independent set, and the chromatic number is at least, always for any graph, is at least the number of vertices divided by the independence number. Okay, so one thing to do then, if you're going to check the chromatic number of a graph, is to figure out what the independence number is likely to be. Okay, so let's look at the graph G(n)(1/2). So here every graph is equally likely. So in an old paper in 1970, Matula proved that it's roughly 2 log n. It was quite precise what he proved, but roughly 2 log n. Okay, and also, but if you're thinking algorithmically, what's the maximum size of an independent set that's easy to find? Well, it turns out that finding an independent set of size roughly log n can easily be done in polynomial time. You just use a greedy algorithm. You pick vertex 1 and you delete all its neighbors. Then you pick a non-neighbor and you add it, and then you delete anything which is the neighbor of something you've picked. And what you see is after k successful steps, the expected number of neighbors is about n over 2 to the k. So once k is log 2n, you sort of run out. But you can argue that you will get to log n. So what we know is then the size of the largest independent set is 2 log n, and it's easy to find one of size log n, but that's about it. So algorithmically, it's a really it seems to be a very difficult question. Can you give a polynomial time algorithm which gives you an independent set of size 1 plus epsilon log n for any epsilon? Epsilon could be 0.000001. Okay? And you can actually do it in n to the log n time just by n to the order log n time just by looking at all sets of size 2 log n. But it seems to elude polynomial time. Of course, to prove you cannot do it, you would actually have to prove p is not equal to np, so that makes it difficult. And even if you prove p is not equal to np, you wouldn't necessarily solve this problem. So it's hard. And all I know about it, there are some negative results about you take some class of algorithms and it fails. And it's not clear why, but still. Okay, no, maybe not possible. Okay, so it follows from Matula's result that the chromatic number is at least n over 2 log n. So what can you do in polynomial time? Well, the same sort of greedy type approach tells you, since it's easy to it's easy to find these independent sets of size log n, you can sort of expect that a greedy algorithm will give you n over log n colors. So again, it's n over 2 log n is what comes from Matula's result. So somewhere between n over, and you can do it in n over log n. So the chromatic number is somewhere between n over log n and n over 2 log n. And this is a sort of mystery for a long time. So clearly, if you cannot find an independent set of size 1 plus epsilon log n, then you cannot find a coloring which is better than 1 minus epsilon n over log n. So I don't know if this could be NP hard, but it's certainly pretty hard. Okay, so for a long time, I mean, well, it's not that long. I mean, it's 20 years maybe, I don't know. Nobody could prove this upper bound. Okay, so it could have been n over log n, but maybe it was. And actually, there was an interim result by Matula and Kuchera. Kuchera and Matula, was it Matula? Which replaced the n over 2 log n by 2/3, I think. So sort of halfway there. Anyway, so the story, wow. So the story goes, suddenly martingale concentration inequalities appeared. Well, obviously they'd been around, and I know some of the people involved in some of these previous results knew about martingale inequalities, but somehow they hadn't appeared in the sort of random graphs community. It's actually quite strange. I mean, Randy obviously knew about them, never used them, right? So here's a very simple version of a martingale. We said no, there's no martingales here, but the consequence of the martingale inequality is you take some random variable z, which depends on n random variables. The important point here is that they're independent. And the condition is that if you only change one of the xi's, you don't change z by more than 1. Okay. And so it follows just from that simple statement that that z is concentrated around the mean, and says that the probability that z minus e of expected value of z is at least t is less than e to the minus something t squared over n. Okay. Sort of geometric result. So this was discovered sort of simultaneously by Shamir and Spencer and Rhee and Talleyrand in about the 80s. And so what it says is that you can actually put t equal to the expectation, so you pay the probability that z or z is 0 is less than e to the minus 2 expected. Okay, so we knew that it was concentrated, but it still doesn't tell you what it's concentrated around. Okay. So the question is, what's the mean now? Once you know the mean, you're done. And so our clever idea of, which is a more inequality, sort of inspired some stuff on concentration inequalities. So Bolabash was able to prove, that in fact, that the 2 was correct using these martingales. And so when you think about, when we thought about before martingales, we say, okay, so we can find a color, we can find 2 log n vertices and color them red, and then we can remove them. But then the problem now is that the rest of the graph is being conditioned. It's no longer a random graph. What are we going to do? So we just sort of gave up. But what the martingale concentration inequalities tell us is that if you have a large subset, then it always has one of these sets of size 2 log n. And so you can just keep happily pulling them out. So the question is, how do you prove that every large subset contains one of these independent sets of size 2 log n? Well, what you need is a clever random variable. And Bolabash used a random variable, which is the maximum number of independent sets in a collection S1 up to Sz, where they only intersect in one vertex. And they're all of size roughly 2 log n. And the point about this random variable is if you flip an edge, it can only change this by 1. And then you just put it into the machine, into the martingale machine, and you get this concentration. And then you know that every set of size, say n over log squared n, does contain an independent set of size 2 log n. And so you just greasily, but we don't know how to do it, obviously, because we can't find them, but in principle, if you spend enough time, you can find these independent sets of size 2 log n, and you color until you're left with n over log squared n vertices, and then you just give them all the different color. And so you've got a coloring of size roughly n over 2 log n. Okay, that's that. And now recently, let me just talk about, So there's been a lot of research recently on, well, so that was Gn1/2. That's a fairly dense graph, has a large number of edges. What if you consider a graph with fewer edges? So if you take GNP, where P is constant over n, where D will be a constant here, what can we say about the chromatic number? So the first thing we expect is that if I take a typical value of P, that there should be just almost every graph in that probability space should have the same chromatic number. And there should be some points, which we call dk, where it's a jump. So there should be this step function. Except at the beginning, where up to sort of 1 over n, there is also a positive probability that it's either got triangles or odd cycles, or it doesn't have odd cycles, and that happens with a positive probability, so it's different at the beginning. So there should be this step function, but that's a big open question, whether there really is one. But Frieze made a lot of progress on this problem in relation to something called KSAT. And then Aklioptis and Frieze, there's almost a, I don't want to sort of say exactly what I mean, but there's almost a threshold. It's not quite what we actually want. Okay. And then Wuchuk actually proved that this is sort of best possible in some sense, that it can take, with high probability, takes one of two values. And of course, what we really think is that most of the time it's just one value. Except for a sort of countable number of points, it should be just one value. Okay, so Wuchuk showed there are two, but we didn't know what the values were. And then recently, Aklioptis and Nauer found out what these two values are, and they are defined, they're about 2k log k. So with high probability, the chromatic number of GNDN is, no, so you take D, oh yeah, so you make, it's about D over 2 log D, not 2k log D. It's about D over 2 log D. Okay. And how do they prove that? Well, the idea is simple. You just take X to be the number of K colorings of G and D of N. If K is too small, the expected number tends to 0, so there aren't any. And if K is slightly bigger, then you can use this inequality, that the probability X is positive is bigger than the square of the mean divided by the expected value of X squared. You have to calculate this expected value of X squared very carefully. It turns out to be omega 1, then you can use Friedgut's result. So the idea is fairly straightforward, but it's actually difficult. It's a difficult proof because it's very difficult to estimate the expectation of X squared. And we extended this to hypergraphs. And there's sort of more work going because it's interesting. What we really would like to do is to nail this DK down. So there's still a sort of a gap between what it could be and what we know it is. And then Koyoglan and Vilenchek proved that, made an improvement in DK. And, oh yeah, so the upper bound comes from the first moment calculation. So you get DK is less than that. And then Koya-Oglan improved that to 2k log k minus log k, whatever that is. And what he's using in this result and the result with Vilenchek is, what's it called? Intuitions from statistical physics. So in statistical physics, this is some version of the Potts model at 0 temperature. And when you're getting near to the chromatic number, you're getting near to some phase transition. And the physicists have intuitions about the structure of the set of solutions. And using, and very strongly using these intuitions, Koya-Oglan and Vilenchek are able to prove the results of Akliopoulos and Nauer. Okay, so it's getting a bit late, isn't it? So we still don't know what the exact value of DK is, but it's known to be within a small constant now. I don't think I can do Hamilton cycles in 10 minutes, so I'll skip that, and you'll have to look at it on film, I suppose. Uh, 10 minutes. All right, let me just do a little bit of this. Okay, so if you're studying optimization problems, you can also look at the, you get a random variable which is the optimal value. And this is a random variable, so you want to know about it and what can you prove about it. So I'll pick, one of the nice ones is a spanning tree. So what is the question? So I take the complete graph and I generate the edge lengths independently and uniformly from 0, 1. So XE is the length of the edge. And I ask what is, and I take Z or Zn, that will be the length of the minimum spanning tree. And I would like to know something about the distribution of Zn. Okay. So let T be the minimum spanning tree and let L be its length. Well, then you say Zn is just the sum of the lengths of the edges. Then you do a nice little trick. You replace xe by some sort of an integral, and then you interchange the integral and the sum, and you do that. And then it turns out you get this sort of nice formula which says that the length of the tree, the expected length of the tree, is the integral between 0 and 1 of the number of components, or the expected number of components in the random graph GNP. So you take that, right? So we have this formula. The expected value of Zn is the integral of the expected number of components. And we sort of got a handle on the number of components, so we can sort of grind this out. And so there's some simple facts will be that, so there's a -1 there, but if p is bigger than, say, 6 log n over n, it's connected with very high probability, and that takes care of the 1. And almost all the integral is going to be accounted for by small, isolated tree components. So we're going to expected value of Zn is going to be roughly this integral between 0 and 6 log n over n of the expected number of isolated trees. And I can write down the expected number of small isolated trees. I can write that down exactly and do a bit of jiggling around, and I get this formula. It's asymptotic to that. And then the nice thing then is that the expected value tends to zeta 3. So I mean, if it tended to 1, it wouldn't be so interesting, but tending to zeta 3 is rather nice. So this was a thing I did in '85, but that proof, my proof was a bit ugly. And this nice proof, which comes from this integral formula, comes from Janssen in 1995, where he proved the central limit theorem for this thing. So this zeta 3 seems to hang around. Okay, so it's a bit out of order. Okay, so what if we try and compute the thing a bit more accurately, the expectation? Okay, with several other people, we prove in fact that the expectation is zeta 3 plus a constant over n, plus another constant over n to the 4/3, plus little o1. And it would be nice to sort of actually continue this, but I don't think I can guess what the little o1 is. But interestingly enough, okay, so you're not supposed to absorb any of this, and they're not particularly pretty. I mean, C1 itself is not too bad, but inside C2 is this psi. And the definition of psi is the expectation of this moment generating function. And the moment generating function is for this integral, which somehow has a Brownian motion in it. So it's very strange. I mean, okay, so having zeta 3 in it, but it's really strange to get Brownian motion into this particular thing. This comes from a sort of a nice paper by, well, there's two papers, one by Aldous and one by Spencer, explaining the relationship between Brownian excursions and these things called Wright coefficients, which have got something to do with the number of graphs with n vertices and n plus k edges. Okay, so I'm nearly done. So, okay, so you can actually, instead of just taking a random spanning tree of a complete graph, you can take an arbitrary regular graph with a little bit of expansion, and then you, instead of getting zeta 3, you get n over r times zeta 3 plus epsilon. So for a bipartite graph, the random bipartite graph, instead of getting zeta 3, you get 2 zeta 3. I don't think I have time to do this. So I've got some pictures. Pity. It's a pity because zeta 2 comes up in this one. Well, it did. Sorry, I cut it all out. So some open problems. Okay, 5 minutes of open problems. So what's the natural open problems here? Okay, well, I've already mentioned this. Find the clique, a big clique in polynomial time, or prove you can't do it. Now there's also the planted clique problem. It's a bit strange. So suppose you've got g(n)½ and somebody, without telling you, puts in a clique of size p. And this is called a hidden clique, and your job is to find it. It could be some signature scheme. Right? So what is known about the hidden clique problem? Well, if p grows faster than the square root n, then it's just enough to check the vertices of high degree, and they will tell you where the clique is. If p is of order square root of n, then spectral methods work. I think you can compute some eigenvectors and look at the components of these eigenvectors. This is along Krivich-Sudakov. But on the other hand, if p is smaller than square root n, there are some negative results, which says that certain classes of algorithms will not work. So the problem then is to sort this out. Either find a non-statistical algorithm, wherever that is, for the planted clique problem where p is smaller than square root n, or prove that it cannot be done. But proving it cannot be done is like proving p not equal to np. Okay, so do the thresholds properly for the chromatic number. K-sat I never mentioned, but that's a similar sort of problem for K-sat. Find the exact thresholds for K-sat. I mentioned, this was some, I'll skip that. So in practice, we solve lots of problems by branch and bound. It's an algorithm, very simple algorithm. It's a search algorithm called branch and bound. And I suppose the question is, can you analyze this on random instances? And the problem is the data gets conditioned immediately. And either there's a trivial argument that it works or it doesn't work. So there's a case here where it's not clear whether it's polynomial time or it's non-polynomial time. And it would be nice to resolve that. So the exact thing is in the published paper. Oh yeah, so there's this question of the simplex algorithm. So there was a lot of work done. So after Kacchian showed that linear programming was in P, there's always this question, but then Clear-Minty showed that ordinary simplex algorithm wasn't a polynomial time always. There was a lot of work done on random linear programs. But so the question is does the simplex algorithm work on random instances? And there were some positive results, but they always use this rather strange algorithm called the shadow simplex algorithm. Whereas really you would like to argue that the ordinary simplex algorithm that you learn, right, would work. The shadow simplex algorithm is the basis of this thing called smoothed analysis. Okay, so finally there's a problem that Van mentioned in his talk yesterday, which is suppose you take a 0-1 matrix, which is regular, in the sense that every row and column has R1s. Okay. So you have to prove that with high probability, this is non-singular. And surprisingly, it's, well, Van can't do it, so it must be difficult. I've already mentioned this, the unit square, and I think I got 50 seconds. Same thing, I've already mentioned the term in the constant beta. Oh yeah, so there's, so the assignment problem is a sort of, basically it says find the minimum weight perfect matching in a bipartite graph. If you put random weights on, it's very nice that the expected value of the minimum weight perfect matching, it grows like tends to zeta 2, and it's a very precise formula. But you can also think of three-dimensional versions, and this is unknown, what the results are for three-dimensional versions. There are some results. You can prove that in the three-dimensional version, the expected value of the optimum, whatever that is, somewhere between a constant over n and constant log n over n, and the lower bound is trivial, and the upper bound comes from a breakthrough result of Johansen, Kahn, and Vu. on matchings in random hypergraphs. Or you could, if you go to Hamilton cycles, you could say, what's the threshold for there to be a Hamilton cycle in a random subgraph of the Q? Okay, so that's it. Thank you very much.
Thank you very much for the interesting talk. Any questions and comments? Okay, so if we have no questions, let us thank the Professor Alan Frieze again, and let me present this